It's common because it's usually helpful to think of chemical reactions as simple, straightforward processes, but in reality, many reactions never finish. Ever. When reactants react to form products, what we usually mean when we talk about chemical reactions, it's technically called the forward reaction. But sometimes there's an opposite reaction that occurs, with the products changing back into the reactants. We call this a reverse reaction. Now, exactly what kind of reactions do this and why is hard to describe without busting out some 200-level chemistry kung fu, but it all goes back to our lesson about Gibbs free energy and reactions that occur spontaneously. Reactions are reversible when they can go forward or backward without any extra energy being used. Remember, this isn't just one reaction happening once, it's billions and trillions of reactions, and some of them might be going one way while others are going another way. And when the forward and reverse reactions occur at the same rate, that's called chemical equilibrium. And even though we all like the idea of balance in our lives, in this case it's not always a desirable thing. In fact, most chemists make their living using tricks to prevent chemical equilibrium, to knock it out of whack, maximizing the concentrations of the chemicals they want to produce at the expense of the balance that nature usually seeks. For example, consider the Haber process for making ammonia from nitrogen in the air. When we discussed it as a redox reaction a few weeks ago, we described it as a one-way complete reaction because that's all we needed to understand right then. But I was lying to you. Sorry, I'd rather you hear it from me than out on the streets. Turns out, the reaction really exists as an equilibrium. As nitrogen and hydrogen react to form ammonia, the concentration of those gases drops, making them less likely to collide and keep reacting. So the rate of the forward reaction slows down. At the same time, the concentration of ammonia rises, more ammonia molecules are available to break up into the reactant gases. And surprise, the rate of the reverse reaction speeds up. Eventually, those two processes reach a point where they happen at the same rate. At that point, there's no discernible change in the concentration of any gas. Nitrogen and hydrogen keep combining to form ammonia, while ammonia keeps breaking down into nitrogen and hydrogen at the same time. Notice that I did not say that the reaction stops. The reaction basically never stops. It's just that we don't notice any changes at that point, because everything that happens in one direction is perfectly balanced out by what happens in the other direction. That's why reactants like this are written with a double arrow, indicating that the process runs both directions. Like if I stand on a balance board, I never stop moving. I just shift my body back and forth to compensate for the motion of the board. When it moves left, I move right, and vice versa. And by doing that, I'm able to stay upright. Hopefully. But sometimes there is, if you will, a disturbance in the Force, and as any good Jedi knows, those things must be put right. Chemical equilibria can be disturbed by changes in the concentration of one or more substances, or by changes in temperature or pressure. We describe these changes based on which way they force the equilibrium. We say a change shifts the reaction to the right if it tends to make more products form, and to the left if it tends to make more reactants form. This was all summarized nicely by a French chemist named Henri-Louis Chatalier, who was born in Paris in 1850. Today, we call his summary Le Chatelier's principle, and it says that if stress is placed on a system that is at equilibrium, the system will proceed in a direction that minimizes the stress. That can happen in several ways. For starters, changing the concentration of any substance in a reaction causes it to proceed in whatever direction restores the former balance. For example, once the Haber reaction is at equilibrium, if you were to add more nitrogen gas to the mix, the existing hydrogen would have more nitrogen to react with. Thus, it would begin forming more ammonia, sending the reaction noticeably to the right until the reaction balances itself again. Removing some of the ammonia would have the same effect. There would be less ammonia available to break down, so the formation of ammonia would temporarily exceed the formation of nitrogen and hydrogen, and the reaction would again shift to the right until the balance is restored. Now here's an ironic side of irony served up for you. In 1901, Le Chatelier tried to invent a process for fixing nitrogen, to make ammonia from nitrogen and hydrogen. But he gave up the effort after the experiment caused a huge explosion that killed one of his lab assistants. 8 years later, the German chemist Fritz Haber, probably the closest the world ever got to a literal evil genius, did just what Le Chatelier was trying to do. And in contrast to Le Chatelier's despair at the death of his assistant, Haber had no problem at all with the fact that his procedure, now known as the Haber process, was used to make chemical explosives which killed hundreds of thousands of people in World Wars I and II. But just to prove that there aren't aren't clear winners and losers in science, the Haber process also saved uncounted millions of lives because the ability to fix nitrogen has made chemical fertilizers possible and basically revolutionized modern agriculture. Haber was awarded the 1918 Nobel Prize for his discovery, but 30 years later he was considered by many to be a war criminal and spent his last years as an object of shame to his family and hatred for many others. Chatalier, meanwhile, despite his great contributions to our understanding of equilibrium, considered his failure to find an efficient method for making ammonia to be the greatest blunder of his scientific career. One of the key achievements that Haber made was figuring out a way to continuously remove ammonia as it was being produced. This allowed the forward reaction to keep going faster than the reverse reaction, basically preventing the process from reaching a state of equilibrium. But changing concentrations is only one part, or actually only 1/3 of the story. There's also pressure to consider. When you look at the equation for the Haber process, for example, you can see that 4 moles of gas react to form 2 moles of gas. So the forward reaction decreases the volume, while the reverse reaction increases it. This is important. Increasing the pressure will then put more stress on the high-volume reactants than the low-volume products, so the reaction shifts to the right, producing more ammonia than it does at low pressure. And indeed, the industrial Haber process is done at 200 atmospheres of pressure. Decreasing the pressure, meanwhile, has the opposite effect. The reaction proceeds in the direction that raises the pressure back to where it was before. In this case, that's the breakdown of ammonia toward the left, where there are 4 moles of gas. Solids and liquids aren't affected